So now let's continue with this concept of heat, and we're going to look at how heat travels through matter. Okay, so for this one, let's look at the computer simulation again. Well, another one, this one here. So let's say that you have water, and well, water and oil, they're going to have different densities. So even though they take up the same amount of space, water is going to have the water is going to weigh more than the oil. So the mass is going to be a factor here. But let's say that, let's see what happens when I increase the temperature of both of these things here. So I'm adding the same amount of heat. Oh, I forgot. I have to include the thermometers. This is going to measure the temperature of the water. This one's going to measure the temperature of the oil. So you add the same amount of heat. If you notice, the oil's temperature increases faster. So here, this is pure water and this is pure oil. And when you add heat to it, the temperature increases. So this is the next thing that we're going to talk about then. So anytime you have a pure phase, meaning it's either going to be a solid or a liquid or a gas. So in this case here, the way that the heat travels through it, so it's going to be, so let's kind of do a picture of a cylinder again. So the cylinder is going to have a mass M, and you're going to add heat to it. So the heat is going to flow in here. And remember, heat corresponds to just like a flame, and that's going to be a form of energy. And what that's going to do is it's going to make and let's say that this pipe here started off at, let's say, 10 degrees Celsius. After a while, after you leave this thing on the flame for a while, the temperature can jump to 100 degrees Celsius. So the fact that you added heat increased the temperature. So in terms of an equation, we can say that anytime you add heat to an object, given its mass, it's going to make the temperature rise, and we're going to write this as change in temperature, or delta T, where delta T just means temperature final minus temperature initial. But there's one more thing. Is this thing copper, or is this thing aluminum, or is it plastic? So depending on the material, that's also going to affect the amount of heat that it can absorb. And so there, the term that describes the material is going to be this new concept called specific heat, which is going to be a little c. So this value for specific heat, you'll find, well, its units are going to be in joules divided by kilograms divided by degrees Celsius. And there should be some values for that in table 15. In appendix C of the book. So for example, you can find the specific heat for water, and then for oil, you'll find those in appendix C. So that's the first way that heat travels. If you have a pure material, the heat, so again here, if you have a pure phase, a pure solid, or pure liquid, pure gas, this is going to be the equation that's going to describe how the heat flows. So you add heat, it's going to make the temperature increase. So let's go back to the computer simulation, and we're going to add more heat here. So in this case, let's see what's going to happen. So we're going to add heat, and let's just ignore this one for now. We're going to add heat to the water. Water is a pure phase, so the temperature increases, but notice what happens when it starts to boil. As it starts to boil, the temperature stays the same. So there's something else happening here. You're adding heat to it, but the temperature is not rising. But what is happening is that it's converting the water, the liquid water, into vapor water. And that's what the next term is going to talk about. So in this case here, in the picture, what you had is a jar filled with water, and then water evaporating. And I think I have a picture. Yeah, here it is here. So here, what you have is a combination of two phases. Inside the pot, you have a liquid, and above the pot you have a gas. And in this one over here, you have a salt water in the form of a solid, and as it's melting, the water is in the form of a liquid. So you don't have a pure phase anymore, you have a combination of two. And anytime you have something that's in a process of melting or evaporating or condensing, there's other phases like besides these, but we're just going to concentrate on these two. Here the temperature is going to stay the same. So the heat isn't going to affect the temperature, so the heat should be unrelated to the temperature. But the other idea is that if you have a small pot of water versus a big pot of water, if you add the same amount of heat, then it's going to take, the small pot of water is going to boil faster. So the mass, how much mass you have, is going to affect how long it's going to take for the water to boil. So the equation that describes this then is this one. If anytime you have a combination of two phases, whenever something is melting, the heat to melt it is going to depend on the mass. The more mass there is, the more it's going to take to melt it. And heat has units of joules, mass has units of kilograms. So we need to make these two units match. So we're going to introduce a constant, which is going to be called L, which is we define as the latent heat, and that's the heat that it takes to melt 1 gram of or 1 kilogram of, for example, water. So let's look at the units then for the latent heat. Latent heat is going to have units of joules per kilogram. And again, you're going to find the different values for latent heat in table 15 in appendix A. No, excuse me, appendix C, sorry. Okay, and actually there's one more thing I forgot. Heat is also going to be given in different units. It can be given in joules, it can be given in calories, or it can be given in British thermal units. So you'll just have to remember how to convert those. This simulation is going to help us to understand how an object's temperature is going to increase when you add heat to it and you let time go by. So you're looking at, this is a container, and inside this container you have frozen water or ice that starts off at negative 20 degrees Celsius. And on the right you have a graph that's going to show you the ice's or the water's temperature on the vertical axis and time on the horizontal axis. So let's let this thing run. So as you add heat to it, notice that the temperature of the ice is increasing. And once the ice starts to melt, then the temperature stays the same. The reason why it stays the same is because now the heat is going into breaking apart the ice bonds to convert it into water. And now once all the ice has been broken down into water, then the temperature increases again. So the thing to notice is that whenever you have a pure phase, temperature is always going to increase. And there, what the heat's going to do is it's going to make the molecules or the atoms move much more rapidly. So as temperature increases, the water molecules here, they're going to be moving more rapidly. And once the water reaches 100 degrees Celsius, then there, water starts to boil at 100 degrees Celsius, and you notice that the temperature stays flat again. And the reason why is because here the heat is not going into making the water molecules move any faster. What the heat is doing is breaking away the water molecules and converting that into a gas. So as the water evaporates, then the temperature stays flat. And once all the water evaporates and you get a gas, then the temperature increases again. So let's try to understand this pattern. Let's go ahead and reset this again. So if we let this thing run, so whenever you have a pure phase and you add heat, the temperature increases. And whenever you have a mix, in this case here, between ice and water, the temperature stays flat because the heat is going into breaking the bonds. So again here, you have a mix of the two, so the temperature stays flat. But now, once you have a pure phase again, then the temperature increases again. So temperature is always going to stay flat whenever you have a mixed phase in the first case between ice and water. But here in this case, you have a pure phase of just water, so the temperature is going into increasing, or to making the water hotter, or to making the water molecules move faster. And we're almost at the next stage. So here again, you have a mix of two phases. You have a liquid phase in the container, and you have a gas phase in the air. So you have a mix between the two. So there, again, the temperature stays flat. So whenever you have a mixed phase, either solid or liquid or gas, the temperature is always going to stay flat while the bonds are getting broken, or also while bonds are performed if you're cooling it down. And once you have a pure phase, now this is water vapor, water vapor, then the temperature increases again. So the basic idea, whenever you have a pure phase, the temperature increases. And whenever you have a mixed phase, for example, water and solid water, or ice and water, liquid water, the temperature stays flat. Or also whenever you have a mix of water, liquid, and water vapor, the temperature stays flat as well.